So welcome back to the second part of this tutorial. In the next step we will unroll the surfaces. Unfortunately, Grasshopper doesn't provide a component for this function. Rhino provides a feature for this. It's called unroll surface, and we have here some options. And we can use this function in Grasshopper with a Python component, but for this tutorial we will use add-ons. There are several add-ons that provide this functionality, among others Wombat, unroll brep, unroll polysurface. This one I think is from OpenNest, yeah. This one from Wombat, the Wombat add-on, and this one is from Pufferfish. You can get these add-ons, can type in package manager. Here you can search for the add-on Wombat right here and click on install. You can do this with the package manager or on Food for Rhino. So here is the Wombat add-on, the Pufferfish add-on, or the OpenNest add-on. And I will continue with the Wombat add-on right here. Here we have the functionality that we can, if we have curves or points on the surfaces, we can unroll them too and use them as reference points or something else. OpenNest is useful when we later want to bring the pieces together on a layout, but I have encountered a problem. With OpenNest, the faces may not unfold the right way around, so I recommend to use the Wombat or Pufferfish add-on for this task. And yeah, I will show you a method to find out if your surfaces are wrapped or unrolled the right way around. Before that, we will unroll the surfaces first. Okay, I will delete these components. Just use these. Here we can see that each object is unrolled at the origin. So now we will construct a grid of points with the same number of points as there are objects, pyramids right here. We started with the grid, so I will use this component. We can use the extend X and extend Y. So we have here our informations. We can right click on the inputs and hide the wires. Okay, here we have a grid. I will construct a point to move this layout in Y direction or in X direction. And then we can set the spacing. Use the area components to receive the centroids, and we don't need the grid, so we can disable the preview. Here we have our points, and now we can create or construct a new point, and now we can construct vectors from the origin to each point, so we receive the same amount of vectors as we have points right here. Vector to point, the origin for input A and the centroids for input B. Now we have our vectors, and when we are creating a grid. With this component we have the list structure of columns and rows, and we don't need this, so we just flatten this list. And yeah, so we have every item in one list. And now we can move our unrolled geometries with these vectors to this position. And here we can see that our unrolled geometries are listed in several lists. So we have here, so one pyramid consists of 4 faces, so we have 4 faces per list. And when we look into our list structure here, we can see that all vectors are in one list, but we need one vector for each list right here, for each pyramid. So we graphed this list, so now we have all the vectors in own lists, and now here the first vector is for the first list right here. So we can use this list structure, and here it's also important to graft this list. Now it works. We have here our objects. We can modify our layout and group this. Okay. Now we have our unrolled surfaces. Here we unroll them with the Wombat add-on. And now we can check if our surfaces are oriented the right way around. We can check the surface directions, and therefore I will show you a method. Don't forget to save your file from time to time. Okay, we start with our unrolled geometries. Here are our surfaces, and we can check them under the display tab. Here vector display X. Okay, so now we need a point on the surfaces. We can get them with the area component. So if we plug this in, now we have all the areas. And to receive the normals or the normal vectors of these surfaces, we can use the surface closest point to receive the UV coordinates and the evaluate surface component. Here are our surfaces. We connect the surfaces right here and the points. Then we have our UV coordinates. We use them right here. Then we receive the normal vector. So this component just pulls the points on the surface. Therefore we receive the UV coordinates, and with the evaluate curve surface we receive the normal vectors. Now we can connect the point to this point input and these vectors to the vector input to receive the vectors. We can also use the vector amplitude component if the vectors are too small to control the size, but in this case it's all right. We can also change the color. With this workflow we can check the surface orientation. So here we can check the surface direction, and now we will check it on the 3D geometry. I will just hide the preview of the unroll. And now we will check the 3D geometry. We can copy this group and use them for these ones. Here we have B-reps and here we have surfaces. So first we have to use the component deconstruct B-rep. And now we receive the surfaces like here. We this component can connect the surfaces here, and here it's useful to decrease the size of the vectors. Okay, yeah, now we can see that the vectors are pointing inwards, and here the vectors are pointing upwards. So if the arrows are pointing inward on the 3D geometry, the outer or the inner surfaces will point up, and the outer surfaces will point down when unfolded. And we have to consider this when we will create the taggings or labeling, so the text on these surfaces. And if you want the text and markers to be visible, the arrows on the 3D geometry must point outwards. If you don't want the text and highlights to be visible, the arrows should be pointing inwards. In this case, it can be the other way around. This is important to note, otherwise we won't have any information later on how around our surfaces are unfolded and in which direction we have to fold. So if you want to flip the faces, you can do this before unrolling with flip. Should be this one. You can find it on the surface tab right here. Then you can flip the surfaces and you have to use the deconstruct component because these are B-wraps and we need the surfaces. Then we can join all surfaces with B-wrap join together. We can test it right here. If we input the surfaces, now we see that the arrows are pointing outwards. Okay, we can use this. Now the surfaces here are pointing outwards and here upwards. So the text will be visible. So keep that in mind. If our surfaces are now correctly unrolled, we can start with further steps. Don't forget to save your file. We will now build the connection parts. For this we need to find out which edge we have to edit and in which direction we have to adjust it. So for this reason we will work with the 3D geometry and roll off points that lie on the surfaces in order to be able to use the points as references right here. We need more space here. I just grouped these components right here. So here are our surfaces. Here we flip them and here we join them together. So we receive the B-wraps. And this is optional as pointed out. And you can also just use these components and connect them right here. In my case, I am using this. And now we will work with the faces. And we want to find the edges that lie on the ground. Therefore, we will deconstruct all faces to receive all edges. Then we can use the component curve middle to receive the midpoints. And now every point represents an edge. And when we deconstruct the points, we can take a look. And here we can find out which point in this list. So these are the points and which points is at Z0. So we can sort the list. Therefore, the smallest value will be on top at index 0. Then we can sort the points. Then when we do list item, we can now use the component list item to receive every item at index 0. And here we are sorting the points. We can also sort the edges and use the list item component to receive every edge that lies on the ground. And now we can use the area component to receive a point on a surface, and we will project this point, so every point on the respective edge with the curve closest point component. Here are our edges, here are our points, and we have to check the list structure again, because we see that we have here multiple points on an edge, which is not what we want to achieve. Okay, here we can see that every edge is in its own list, so we just have to graph it. And then we have the same list structure and can use them here. All right. Can hide these. And now we have our points on the edges and the upper points. Why are we doing that like this? Because when we connect these 2 points to a line like this, here we can see all the lines, then we see that this line is perpendicular to the edge. Okay, in this perspective it's quite difficult to see that, but this line, or maybe when we go to the top view, we can see that this line is perpendicular to the edge. And this is important when we want to use this point on the surface to move towards the surface center, and we can use these 2 points, unroll them on the surfaces, and then we know the direction where we can position our texts or our connection parts. So these are the 2 points we need, and we will unroll them with this component. Here we have our B-reps. We have to check the list structure again, and here we have our points. And now it's important that one B-rep consists of 4 faces, and we have for each face here 4 points and here 4 points. So to receive every point of the B-rep in one list, we can use the trim tree component. And then we can see that we have our previous list structure, and that's because we can take a look on the list path. Here we have 0, 1, 2, 3, and then again 0, 1, 2, 3, and here we have the path. Okay, we can simplify it. We have deleted all unnecessary paths, and on the first layer we see that these 4 lists has the path 0, and then the next 4 lists has the path 1, and therefore all these 4 lists will merged or trimmed in this structure. So we call in the last index or the last path structure. So this was our list structure, and now we have it again. So we can use the the trim tree component for this. And we have to use this also right here. Now we have our list structure, and these are our points. So the first list represents, for example, this pyramid with 4 faces, and here 4 points, and also here 4 points. Now we can merge all points together. Okay, here we have used the simplify component, and therefore the path names, I will just call it like this, is not correct. So here the path consists of only 1 number, and here we have 3 numbers. So we can just simplify the outputs right here. So we have the same path names. And then when we take a look into the merge component, we see that it works now. We have 8 items in one list, because here the first list is merged with this first list. All right, now it works. These are our points. And we can connect our points to the point input right here. Okay, nice. So don't forget to save your file. And here are our points. We can display them. They are unrolled on the origin. And now we test it with a move component. We just copy and paste this one and connect our points. And now we should see our points. Yeah, it worked. Okay, in this part we will create the connection parts. If we take a closer look, we can go to the top view, and we need to fold this geometry on this edge, on this edge, and on this edge, and we need to connect the geometry with this edge and this edge, and therefore we have to create a connection part right here, and we also have to create connection parts on these 4 edges to glue the geometry on the ground if we want to. And yeah, we will start with this edge. Just deconstruct. We receive our BREP as surfaces, so we don't need to deconstruct it. We can just use the list item component. And here we have our first surface. If we selected another surface, then we can change the index. Okay, then we need to deconstruct our faces and use another list item component to receive the right edge. And here we have to find the right edge. Okay, in this case it's 3. Here we have our edge, and now we will use this centroid and project it onto the edge, so we get the direction and can modify this edge. Therefore we will use our points, and these points are structured, so we can use the list item component and find the right structure. So it starts with the centroid, then the point on the edge, the point, the centroid, the point on the edge, and so on. So we can we see that there is a pattern. We can use the merge component and use every second output. These are our centroids. Then we will use a new merge component for the other points. Now when we use the list item component, these are the first centroids. We can use them right here. So we have here the centroids and the edge. Now we will use curve closest point. Curve closest point, and project the point towards the curve. And with this point right here and this point, we can create a line to visualize it. Yeah, and these are the directions. We need a vector, so from this point to this point. And we will unitize the vectors. We can also do this with the unit vector component, or we can type in true. This will do the same. You can unitize the vectors, so the vector length is just 1. Now we can move our edge. Okay, now we moved all the edges and we can control this. And we can control this with the multiplication component. Now we can control it, okay. And now we want to scale this edge down, so we use the scale component and use the middle point as the center. We will use 0.75 as the scaling factor. Loft these two edges together. Use the merge component. And merge these two together. If here is a problem, then the list structure might be not suitable and you have to adjust something. And now we will create these connection parts right here. I will group this here. Okay, now we want to find these edges, and we can do this with the points we receive right here. And therefore we have to here we have the points, here we have the edges. And now we can use the curve closest point. Here we receive the distances, and we project this point on every 4 edges. And if the distance is 0, then we know that this is the edge we want to use. Here we can see we have 4 points for the whole geometry, and here we have 4 curves for just one surface. Therefore, we have to graph this list. So we have 1 point per list, 1 point per surface, and here we have 4 curves per surface, or 4 curves per list. Now it should work. We can connect these inputs. Okay, we can sort them and use list item to bring this here, to bring the smallest distance on top to index 0, and then we can use the list item component with index 0 to receive the items. Now we can sort our edges, and here our edges are sorted. We can receive them with list item index 0. So So these are our edges. Now we need to receive our directions, our vectors, and therefore we can just use the centroids and these points. When we connect them together to a line, we can see that here we have all the directions. So instead of using a line, I will use a vector to point, and I will use these points as input A and these points as input B. We can unitize these vectors. Now we can move our edge and adjust it just like above. We can use multiplication to adjust the amount. And here we can see that there is a problem. So we just need to graft this here. So every vector is in one list, and here also, yeah. Okay. We need to reverse this vector, so we can use reverse. And therefore we can reverse the direction. This looks fine. Then we can scale it. I will just copy these components and use them. So here we scale the curve by 0.75. Merge these two together. Everything works. All right. Now we can just merge every surface. So starting with our surfaces right here, merge them. Merge these connection parts and these ones, and we can just flatten the list so that every item is in one list, and then we can join and use BREP edges and can hide the preview, and here we have our outer curves and our inner folding edges. Okay, for the next step we will create the labelings, markings or taggings. We will use the text on surface component, therefore we will need these points. We will start here and then moving these points towards the center. Therefore we need a vector from this point to this point, and we need the points. First we will move these points with these vectors, can unitize the vectors and use the multiplication component, or we can also use amplitude component. Then we have to modify this point to move this point, for example, in this direction. We will rotate this vector. Therefore, we need an axis. We will just use the unit Z component. Then we need an angle, 90. And right click on the input and choose degrees. Maybe it's my minus 90. And then we can move this point again, connect the new point, and use also an amplitude component. I will do the same, but reverse this vector. Now we can create a line from this point to this point. You can hide this one. Now we have a reference line or reference lines or baselines. You can use them right here. And the depth should be 0. So our surface is here. Here we can use it. Now it will be projected, and we need to adjust the font size. Can receive the edges, join the curves together, disable this preview, and now we have to create a text. So every surface has an own ID, so we can recognize it. To create the text, we can use the list length component, and for example measure the length of these lists. So here we receive that we have 4 items per list. Then we need to measure the amount of lists we have here. We can achieve this with different methods. I will just use list item to receive only 1 item per list, like this, and then flatten the list, and now we have every item represents 1 list. So here we have 1 item per list, and then when we flatten it, we have 9 lists. So when we use list length, we have 9 lists. So these are our informations which we can use to create a text. For creating the numbers, we can use this series component, and for the text we can use the char sequence component. We have 9 lists. We need 9 numbers. The list starts, the series starts at 0. We want to start at 1. So every pyramid has a number. So we have 9 pyramids. Every pyramid has a number. And then we want to give each face an ID. So for example, A, B, C, D. And here also A, B, C, D. And therefore we need to know how many items we have per list. We have 4 faces. So we use this list component. The count is here. And we have this here. We have to graph this. So first pyramid is list 1 with number 1. And here the first list says A, B, C, D. And now we can merge these 2 lists. Oh no, not merge them. We need to use this component. And here we can see we have the first pyramid with face 1, 2, 3, 4. And we can create additional things like this. We can simplify it. Okay. We can use this as our text input. So for the last step, we need to export our drawings. Here we have the creation of our geometry, and here are our preparations. And we will provide the script for the second part. Can also use other types of grids, for example, these ones. Here we have 4 faces, so we need to consider that we merge here 4 points. When we use the triangular grid, I will demonstrate it. Then we can see that the geometry is broken, and therefore we have to take a look right here. We have only 3 faces, so we use 3 points. And now it worked, but here's a problem. And this is because we have here a different amount of cells. Here we have, I will just use 3 by 3, and then it works. So if we use other numbers right here, we also have to adjust our layout in X and Y direction. So keep that in mind. And this looks fine. And we can also try out this one. Here we have 1, 2, 3, 4, 5, 6 faces, so we need more points. And now this also works just fine. Oh no, here we have a problem. Now we have to take a look what's happening here. Okay, I found a problem. It's here's everything fine. It's because of the attractor point, just located right here. And the deformation right here is too extreme, so when we move the point closer to the geometry, also in this direction, now we can see that the geometry or the unrolling is working. Alright. So you are able to use different types of grids. Keep in mind that you have to adjust the layout if you have different amount of cells, and keep in mind to adjust these merge and list components. If you have 4 faces, you need 4 points, so 4 inputs right here. So in the last step, I will show you how you can export your geometries. And to adjust the size of our geometry, we can just use the scale component. And here are our text curves. Now we are able to scale our geometries. I will just use the factor 1. And we have to disable these parts right here, and we can also scale them. we want to, we can hide the wire. And of course, use the same factor. And now we can adjust it. And for reference, we need the size. So this is the size of our paper. So we have to keep in mind that here in Rhino should display millimeters down here, or you can go to the properties settings, go to units, and here it should be set to millimeters. So these values are in millimeters, and now we need to scale the geometry. I just double-clicked on the output to receive a relay. And now we can scale it, can move, construct point. Now we can move our layout, and we need to adjust the first layout and decrease the spacing. Now we can increase the scaling, or as an example, I will just leave it like this. Okay. Here we have our curves and this rectangle. In this case, we can increase the text size. So right here. Okay, you can arrange everything in different layers. I will just bake all the curves in the default layer. And it's important to also bake this rectangle curve. Now we have our curves in Rhino, and we have to select these curves, go to File, Export Selected. We have to choose PDF. And here we have some options. When you are exporting, go to the top view or choose the top view right here. Then go to Extend or to Scale. Now it's set to Scaled Fit. You should choose this one. And make sure that the background color is disabled. And choose the width, the line width to hairline. Now you can export it. So feel free to ask if you have any question, and have fun.